Hello everyone, I am Dr. Hana Alghamdi, an assistant professor in the computer science department at the UKU University. I have finished my PhD at Trinity College Dublin in January 2021, and today I will present my thesis topic and contributions. I will start with an introduction, giving a context of the problem and motivation, and then I will present the research problems and scope, and next present the contribution and publications. Many applications involve high-level image analysis and integration of complementary information taken from different imaging resources to present them in a single coherent informative image. An example is presented here in the slide, where a large number of heterogeneous images distributed on the internet that exhibit overlapped scenes are used for 3D reconstruction building. Two problems arise in this integration process: the geometric alignment and the photometric alignment. The geometric alignment is commonly referred to as image registration, which is a fundamental task in image processing. And it is used to geometrically overlay two or more images of the same scene, possibly taken at different times from different angles and different devices. The other problem is photometric alignment, and it refers to the color transfer. And it is the process of matching color statistics or eliminate color variations between images that can happen due to illumination changes or using different cameras, or even using different in-camera settings, or maybe tonal adjustment done by the users. It should be noted that the algorithm, the alignment that given by the image registration algorithms can never be accurate to the pixel level, and it may contain mismatches and errors, which makes a direct color matching of pixel to pixel is an unfeasible solution. So the problem of how to match the colors of images must be tackled differently. And the work undertaken in this thesis aimed to contribute to this domain, the photometric alignment. So what is example-based color transfer? It refers to a process of changing the colors of input image, denoted as the source image, so that they match the colors of example image, denoted as a target image. In many computer vision applications, such as image mosaicing or image stitching, where there is a shared content between the images, images here are required to have consistent colors. In these cases, color transfer methods can be used to harmonize and eliminate the color variations. The figures on the left are examples of this type of transformation. Also, color transfer techniques can be used to transfer the color feel and look of one image to another image. And the purpose of this transformation is to create artistic style images. And here in this type of images, there is no shared content and there is no correspondences. And this color transfer problem is a fundamental process in film post-production. So in the case of the same scene, the performances of the method can be measured using metrics. So we have metrics to measure the performances of algorithms. And in the case of different scenes, each method produces a different output style. So we need subjective user studies to evaluate the performances. In this thesis, we focus on color transfer between realistic images that exhibit overlap scene, where pixel correspondences are available to guide the color transfer process. Applications ranging from mosaicing or stitching of photos, street view maps, panoramic images, or satellite imagery, also medical imaging and visual navigation, or even time-lapsed video like the one shown here, where the frames have shared content, but they are taken at different times with different illuminations. So a popular approach in color transfer is to formulate the color transfer as a problem of transforming statistical distributions, where the actual probability density function PDF of a target image is transferred to a source image. This is known as distribution transfer problem, and it is the main interest of this thesis. However, most color transfer methods in the literature do not scale well in high dimensional spaces, and that due to the increase in computational complexity associated with the increase of the data dimensionality. While the ability to fuse different information such as spatial and color, as well as the directional information, would enhance the image descriptors and would improve the quality of the result. But that would be a challenging problem to the current color transfer method. So this implies the need for transfer functions that are scalable to multi-dimensions and suitable to parallel computation. Recent algorithms based on the idea of minimizing the distance between the distribution prove to be very efficient tools for a wide range application in machine learning and computer vision. Of particular interest is the method that based on the optimal transport and the L2 divergence cost functions. However, optimal transport has not been investigated in high dimensional, and L2 divergence-based algorithms do not scale well in high dimensional space. This slide shows the landscape of publications of related fields and our contributions. One of the first color transfer algorithm was example-based technique proposed by Reinhard here that matched the statistic of a target and the source color distribution in uncolorated space. Since then, many other statistical approach have also been proposed along with histogram matching and optimal transport. And also when the target and the source images capture the same scene, many techniques have been proposed to take advantage of these correspondences to improve the color transfer result. In the same time, in the image field, image registration field, Jian proposed the successful L2 framework that inspired so many later methods, including color transfer method. In this thesis, we extend the work of L2 and optimal transport as well as kernel regression to tackle the high dimensional distribution transfer problem. And our work here shown in red. So to propose a new example-based color transfer method, several questions need to be addressed. First, how to estimate a transformation function that match high dimensional probability density functions and suitable to parallel computation. Is it possible to solve the color transfer method using a high dimensional representation that includes spatial and color information and reserve local structure? And how to estimate a transformation that is accurate enough to match the color of the target image, and how to estimate a transformation function that preserved most of the structure of the source image and also allows denoising and artifact removal, and how to estimate a transformation function that take into account the pixel correspondences when they are available in matching the high dimensional distribution functions. This is an overview for thesis contribution. We will go in depth one at a time. So the main contribution of the thesis is to tackle these questions and to introduce high dimensional distribution transfer functions with statistical techniques such as optimal transport, L2 divergence, and kernel regression technique, namely the Nadaraya-Watson estimator. L2 here is flexible to work with and without correspondences, and it provides a smooth estimate of the underlying function. And Nadaraya-Watson take advantage of the correspondences in its formulation and provide a smooth estimate of the underlying function. On the other side, optimal transport, where doesn't take into account when computing the solution any available information about correspondences, and the solution is always increasing, an increasing function by definition, and it is not smooth. And we show that we can smooth the optimal transport using a smoothing technique as a part of the algorithm. Inspired by the 1D iterative approach implemented in algorithm proposed in the literature initially as an approximated solution to optimal transport, we propose to follow the same approach and solve the high dimensional distribution in a 1D subspaces using an iterative projection approach. So we iteratively project the point values originally in high dimensional space to a 1D subspaces, creating two data sets, 1D for the source and the target images. And next we find the solution, the 1D solution of a choosing transformation function, and then propagate back the solution to the high dimensional space, and we repeat this operation in different directions in 1D subspaces until convergence. So here the 1D transformation are independent of each other. Hence, the process is suitable for parallel computation. In my thesis in chapter 3, I have done a simulated experiment, and I compared and visualized how each method behaves in 1D case, and also compare popular approaches proposed in the literature that tackle the high dimensional using the 1D optimal transport. The thesis is online. I put a link in the references at the end of this presentation. You can locate it and download it. So our proposed transfer function are guided by high dimensional point representation, encoding content information such as color and spatial information, and also local structure. And to show the potential of these mappings, we applied to color transfer field between two images that exhibit overlap scene. In our experiment, we solved problems up to 125 dimensional space. Our high dimensional constructor implies a new reconstruction step, and due to these steps, it allows denoising and artifact removal as well as color transfer. We conducted this extensive experiment, and evaluation consists of using numerical net metric, also summary descriptive statistic, and statistical significant test and visual analysis too. So the first framework that has been explored in my research is optimal transport between PDFs. So it's a good idea to give a brief background. What is optimal transport and how to formulate the problem mathematically? Okay. So let us consider an Euclidean space of dimension 1 for now to ease the representation. Suppose that in space R, we have observations associated to random variable X, and we have a second set of observation collected in the same space, the same Euclidean space associated to a second random variable Y. The aim here is to find the function phi that map X into Y. We can visualize the problem to solve in R2, where we have X here and Y here. So we have like a 2D problem. This is the phi that map X into Y that we need to estimate. And from the observation that we have, we can estimate the PDF for each variables using histograms or kernel density estimation. This is another visualization in R2 of the problem where our F and G are now marginal PDF associated with unknown joint density function. This unknown joint density function captures the interaction between X and Y, including the mapping phi that we want to find if it exists. In terms of optimal transport, there are two formulations, Kantrovich formulation that estimates this unknown joint probability density, where G and F are the marginal PDF associated with this joint PDF. And this joint PDF is estimated by minimizing the expectation of cost C that can be chosen as a distance between X and Y multiplied by the mass function. And it returns the joint density function, or we can call it transport plan, that gives the minimum total transportation cost of transforming F into G. And the other formulation is Monge formulation, and Monge concerned with estimating a one-to-one mapping as shown here. So send 1 point from X to 1 point to Y. Here there is a split of mass. 1 point of X can be sent to multiple points of Y. So there is a splitting in the mass. And we are interested in finding the mapping, the one-to-one mapping, because this is what a proper function for color transfer context. All the pixels that have the blue color need to transform to a corresponding color. So we don't want to split pixels. So Monge cost function estimates the optimal map phi that transport the source distribution into the target distribution with minimum total cost. The cost C here can be chosen as a distance between X and Y, as I explained. We choose the Euclidean distance, and this cost function that return the minimum total cost called Wasserstein distance. And the Wasserstein distance cost function is very much used in color transfer problems and also other applications such as deep learning. You probably heard about Wasserstein GAN that uses Wasserstein distance as a GAN loss function. So the total cost of moving a mass from source point X to a target point Y is induced by the product of the source point mass function by the distance between X and the target point Y, to which the source is transported. Phi of X is our Y here. Luckily, there is a closed form solution for this equation when we are in dimensional 1. So when X and Y in R space, we can find a closed form solution. So when we take this equation and integrate both sides of it, we are using the PDF, we get the CDF, which is the cumulative distributions. Then from here, using the CDF, we can estimate the phi by taking the inverse of G. And this estimated phi defines the optimal transport map for the Monge problem that transports the mass of minimum cost in such a way that associates each X to a single point Y. So there is no mass splitting here. And because due to the simplicity and the explicitness with which a solution can be obtained in this setting, it has been used to tackle high dimensional problems in different contexts in the literature, because this equation, this closed form, alleviates the need for optimization. We can find the solution using PDF we estimated from histogram, or and we get the CDF, the cumulative, and we can induce the mapping using this equation, simple equation. So here we propose such algorithm proposed in the literature that tackle high dimensional. So when we go to higher dimension, more than 1D, this equation, the closed form, is not available. It's not possible. So Bete and Ital and Rosanne Diot propose the iterative distribution transport, the IDT algorithm, that uses this simple equation iteratively instead. So as explained, this approach that iterative projects the point to 1D subspaces and find the solution in 1D. So we can use this example, this equation, simple equation, and propagate the solution to high dimensional and repeat the operation with different direction in 1D subspaces until we converge. And other approach proposes is the algorithm sliced versus time distance, use the same projection approach, but the difference is they do not use estimate histogram and CDFs. They sort the points. So it's considered like quantile matching. So this is CDF matching, here quantile matching in slice versus time distance. You can use this algorithm or the slice versus time distance. So in our first paper called patch-based color transfer with optimal transport, we propose a new color transfer with optimal transport, transform the color of source image to match color of target of the same scene. Because our motivation, what is the motivation? Because, you know, in current color transfer methods, the transfer process, when it's performed in the color space only, it doesn't consider that coherent colors should be transferred to neighboring pixels. And this can create result with blocky artifact and emphasizes JPEG, compression blocks, or increase the noise. So in our proposed algorithm, we extend the 1D projection approach, which is the IDT or the slice versus time distance, using image patches as samples in high dimensional spaces rather than using the RGB triplet in R3. And we do this by encoding overlapping neighborhood of pixels containing color and spatial information. And since several recolored candidate is generated for each pixel because the overlapping step, we define original procedures that merge these candidates, and this procedure allows denoising and artifact removal, as well as color transfer. So our pipeline, the first step is combine the color and the spatial information. We incorporate the original pixel position in the grid coordinates of the image, the global coordinate, where the color with the color information. So the pixel now, we take the color and the position and concatenate it in one vector. Now it resides in dimension Rn, where, for example, if we use the color space RGB, so the RGB is 3D and the pixel position is 2D. When we concatenate it, we have 5D space. And adding this spatial information, we now, the Monge formulation now minimize the following costs. There is a part to concern the color, and there is a part concern the spatial. So Monge formulation now on the combined color and spatial information minimize the distance in the color space and in the spatial space. And F and G are now the high dimensional distribution in Rn, R5, for example. The second steps, we do data normalization. So so here we experiment because we have overlapped batches. So we experimented with using only the color and also with combining the spatial and color. In the case when we combine the spatial and the color, we have the color values range from 0 and 2055, and the spatial value can be anything depending on the size of the image. So in order to produce consistent results, regardless of the size of the image, the color and the position coordinate are normalized both to lie in between 0 and 255 to create this hypercube in Rn. And then we stretch this space in the direction of the spatial coordinate by a factor W to make it harder to move the pixel in the spatial domain than in the color domain. Because since we are focusing in transferring color between images of the same scene, we know that the scenes are overlapped. Next step, we create the patch vectors. We encode overlapping neighborhood. of pixels to preserve the local topology information. Starting from the origin of the coordinate system of the image, the upper left corner, we use a sliding window operation of window size d by d, which was 5 by 5 in our experiment, to extract the overlapping patches. And from each patch, we create this high dimensional vector in our by concatenating all the pixels in the patch with their dimensional features, color only here or color and position. So each patch corresponds to 1 point in, for example, here 50 dimension. And this patch, when combining the position, correspond to 1 point in 100 dimension. I should note that we experimented with local coordinates where we extract the patches, and we consider each patch as a mini image where it has its origin of the coordinate system. It has its own origin, which is the upper left corner of the patch. And we calculate the pixel coordinate and position in the patch based on this origin. We found in the experiment that using local coordinates doesn't provide any improvement in the results, while using the image global coordinate improve the results. So we stick with the global coordinate. Step 4, we use the iterative distribution transfer using optimal transport, 1D, the closed form in 1D. So iteratively take the high dimensional value nouns that we constructed and project them in 1D subspaces, creating 2 data sets for the source and the target image. Next, we find the 1D solution of optimal transport and then propagate back the solution to high dimensional space, and we repeat this operation with different directions in the 1D subspaces until convergence. The last step is merge recolored candidate. So because we have overlapping regions now between patches, so several recolored candidates are generated for each pixels in the source image. We compute the average color value from the candidate and use it with conjunction with the original positions in the image to create the output recolored. So the changes in the positions value that we incorporating in the our package, we discard them. We take only the new colors values and use it in conjunction with the original position of the pixel to create this output recolored image. And this procedures of merging with average operation allows denoising and artifact removal as well as produce smooth color transfer. So here we provide a qualitative evaluation of our approaches, noted here with the name ours C for using color only, and ours C B for color combined with positions. And we compare our approach with the state of the art. All the state of the art solve the problem in 3D color space, and our algorithm solve it in 100D space that's composed by using the color space and local structure. In this evaluation, we use image pairs with similar content from an benchmark existing data sets that include registered pairs of images, source and target, taken with different cameras and settings and different illumination and recolor size. So they are registered. So the geometric alignment is done, and our algorithm is responsible for photometric alignment. To assess the recolor results, we use 4 metrics: the peak signal to ratio to noise ratio based on R. Where is it here? And the structure similarity index, and the color image difference, and the feature similarity index. These metrics are often used when considering source and target images of the same scene. We show here the plot that carries summaries and a lot of statistical details, but please do refer to our paper or the thesis for tables of detailed quantitative results. All the metrics here show that our solution that incorporates the color and the spatial information outperform the solution of using the color only. Okay, and all metric. So we have this result here. The last two box shows the using the color only and or using the color and position. The CID metrics, the lower values are better, and the rest of the metrics, the higher values are better. Also, all the metrics in the box plot show a significant difference in the performance between our approach that use combine the color and the position, and the IDT approach, the optimal transport that solve the problem in color space only. You can see it in all results. Here, this is the IDT. And when we compare our algorithm with the state of the art, other state of the art, our method is competitive with the top three methods, BMLS, L2, and BMLS. And they are greatly overlap with each other. The median shown here as horizontal black lines, and the mean shown in as a red dot. They are the highest. First, they are the highest among all algorithms and very close in value. And using statistical tests, we find that our approach with the top three method are considered equivalent in their performance. So this is in terms of metrics, the numbers. In terms of visual evaluation, we provide this figure here. For clarity, the results shown here are presented as image mosaics. So, for example, I have the source image and the target image, and I create this mosaic by switching between the target and the transformed source. You know, the output of the algorithm, column-wise. So one column comes from the target and one column comes from the source. Before the transformation, you can see column differences. After the transformation, you should see a single image. There is no differences in the column. And this indicates that this image, how effective this color transfer image. Does it match the source and target, or there is a differences? As can be noted, the optimal approach first, we use the optimal function. It doesn't take into account any, in its formulation, by definition, it doesn't take into account any correspondences. And, but when we incorporate the color and the spatial and the neighborhood information, it does outperform the original optimal transport solution that's solve the problem in the color space only, and it does elevate the color differences better than IDT. And compared our approach with the rest of the state of the art, our approach is better than the top methods. The rest of the method, actually, I'm comparing with all the methods here. So it's better in elevating these column differences. Even when L2, this is L2 proposed by Grogan, it does use the correspondences in estimating the solution. So it should give extra strength to the algorithm, but our algorithm that doesn't actually take into account any correspondences do better than L2 in 3D. Here we have a more qualitative evaluation. We picked the top method that give us a higher scores in terms of metrics, and we compare the result with our results visually. While BMLS and BMLS provide good results in terms of metrics, they actually produce artifacts in the output image because there is a registration error. So these two methods, the color method, they are not robust to the registration errors. This, the benchmark, this data sets have source and target registered images. But as I explained earlier at the beginning of the presentation, the geometric alignment algorithm doesn't provide accurate registration, and there is errors and mismatches. So a good algorithm is an algorithm that is robust to registration error. So BMLS and BMLS provide high scores in terms of metrics, but visually they provide artifacts. The metrics that use in color transfer, they assume that there is a correct registration, so they do not pick up these artifacts in computing the scores. But so that we need like do a visual analysis too, not only using metrics. Compared with our results, our algorithm doesn't provide these artifacts. It is smooth, as can be shown here. This result here using the color only, and this result using the combined color and spatial. Because the merging step, our algorithm creates a smooth color transfer result and elevate the JPEG compression artifact and noise compared to other methods here, as we can see here, and you can see the result of full L2 in 3D. The result of our approach is smoother and remove the artifact and JPEG blocky artifacts. However, one limitation in our approach, we can find it here. Though I just need to mention that here in this images, we have a motion. It's not still image or a different object. For example, an elm, we have a different car, completely different car. And our approach successfully transferred the colors with no problem. And also in Mart, there is a motion here. So the two image is not exact. There is a motion between the two image, and our algorithm can correctly transfer the colors between a moving object. But one limitation is when we have a very big changes between the two images, the source and the target. And we can see it here in the building where there is a big change, motion here between the two images. In this case, when we combine the position, our algorithm creates a shadow artifact. While when we only use the color, it doesn't create this. So when we combine, in general, and in conclusion, when we combine the position and fuse extra information in the to create a high dimensional descriptors, it does improve the color transfer. But we have the problem when we have a big changes between or a big motion between the images. It would create this shadow artifact. In the next work, we tackle this problem. We remove this shadow artifact because we still want to fuse different information and we want a better result. So next, batch-based color transfer using SIFT Flow. Here, we improve over our previous approach by encoding by using the SIFT Flow. We extract the correspondences. So first, before why we use SIFT Flow, optimal transport doesn't take into account any correspondences in its formulation and treats the correspondence as a separate database. So what we did, since we are using overlapped scenes, there is correspondences, and we want to make use of these correspondences between the images because it may overcome the limitation that we faced earlier. So in this paper, we propose to estimate these correspondences using SIFT Flow method. So the SIFT Flow method estimates the dense spatial correspondences by robustly aligning complex scenes pair containing significant spatial differences. Okay, so it's not optical flow. Optical flow assumes that there is elimination. The same. It's optical flow depend on the fact that have the same illuminations, but here we have the problem that we have different illuminations. So optical flow will not work here. SIFT flow can work here, so we use it in our algorithm. So basically, we improve the data preparation step in our previous algorithm, and we define the batches using this SIFT flow descriptors. And when we compute the spatial correspondence, we incorporate it in our encoded overlap neighborhood. And this new formulation, now our patches have the correspondence, the corresponding position, makes the optimal transport implicitly take into account like correspondences. So it does improve the transformation output, it does affect the transformation here. And our second contribution here to introduce smoothing as part of the iterative algorithms that solve optimal transport in 1D, namely the IDT and slice versus time distance. So the first step, we combine the color and the spatial correspondences. So assume B is the 2D grid coordinate position of the pixels in the target image. Okay, and WP is the computed flow vector using the SIFT flow method. The corresponding position of the pixel in the source image can be computed by adding P and WP. We compute this value and we concatenate the color and the new position for the pixel in a vector 5D. In our paper, we use RGB color space, and so it's 3D, and the position is 2D, so we have 5D space. Next, we do the data normalization. All the position coordinates and the color are normalized to lie between 0 and 255 to create a hypercube in 5D space. And we stretch the space in the direction of the spatial coordinate by a factor equal to 10 to make it to make the pixel's position influence the computing mapping bigger than the color. So it is like force the algorithm to match colors with the same pixel positions. Next, similar to our previous approach, we encode the overlapping neighborhood of pixel to preserve local topology using sliding window operation of window size 5 by 5 to extract the overlapped patches. And from each patch, we create the high dimensional vector in R125. So our dimension now in 125. This comes from multiplying the 5 by 5 by 5 here. And then because the size of the patch is 5 by 5. The step 4 is the iterative projection transfer. We, as explained early, we iteratively project the point originally in R125 to 1D subspace and find the 1D solution of optimal transport and propagate back to the higher dimensional space. And we repeat this operation with different directions in the 1D space until converges. But at each iteration, before we go to the next iteration, we take the estimated correspondences that comes out from the optimal transport function. So we have X and the transformed X using this 1D optimal transport. We take all the estimated correspondences and we feed in them to the non-parametric Nadaraya-Watson to create a smoother mapping. So in this figure, we see that this is an example of one iteration, 1D iteration. We have the optimal transport. We see that it's not smooth, and we smooth it using the Nadaraya-Watson. And we have H, the bandwidth that affect the smoothing. So when we, this figure shows different result when we choose different H here. Too much, too high value for H can remove the detail of the image. And too low value, it doesn't do anything, actually, it doesn't smooth. So we need, we actually fix H with 10. We find it that's the best value, you know, for all the images. So we fix it. We experimented with value 10 and we fix it. Merge, we can also, actually we can use equation. We can optimize H, but for simplicity, we fix the value. Merge, the next step is merging the recolored candidate because they overlapped batches. We merge the candidate and use it in conjunction with the original position of the image to create the final output recolored image. Here we provide the quantitative evaluation. Our algorithm here denoted by optimal transport in W because we smoothed it with Nadaraya-Watson. We solve the problem here in 125 up to 125 that combine color, spatial, and local structure. In conclusion, the quantitative metric showed that our algorithm, in terms of numbers, similarly perform with, you know, have a similar performance with the top methods, that is BMLS, L2, and our previous approach, and outperform the rest of the state, including the IDT, the optimal transport in color space. But please do refer to the thesis for tables of detailed quantitative result and analysis and significant statistical tests. Here we provide the qualitative evaluation. We can see that our approach here, optimal transport with the Nadaraya-Watson smoothing technique, is successful in removing the column differences better than all the rest algorithms, including our previous approach. Yeah, so it's improved the performance over our previous approach. And yeah, so this is figure shows the quality of the color transfer. Here we examine the noise and the JPEG artifacts. Our algorithm is, as we can see here, is robust to registration. It doesn't produce any artifacts or distortion like BMLS here, and it does a smooth color transfer. And also, you know, our first motivation why we have used SIFT Flow is because to improve the result of our previous algorithm that create shadow artifacts. So our current algorithm eliminates this shadow artifact when we have large motion between images. So example here, building. With PCT OT, we can see some shadow here, but our new approach here that use SIFT Flow correspondences incorporated in the patches eliminates these shadow artifacts. And also, due to this, you know, the smoothing techniques, our approach keeps the original structure of the source image and provide like a smooth result, better actually than BMLS and L2, and remove these JPEG artifacts and noise. Our next work is iterative Nadaraya-Watson distribution transfer. So one application that has been recently become important research topic is light fields. We have like in our department in TCD, we have a group that work on the light field light field images, and the popularity, the increase of the popularity of this technology is because the availability of the light field camera. This special camera extract images with an extensive depth of field, representing different view point of the same scene. However, these images, extracted views, suffer from several artifacts such as color discrepancies. So we need to use color transfer method to correct the color. When the source and the target images from the same scene, correspondences, of course, can be found and can be used to guide the process of recoloring. And here we found the SIFT Flow algorithm is well suited to match the densely sampled pixel-wise SIFT features between the two images. So in this work, we propose the iterative Nadaraya-Watson distribution transfer algorithm, which is inspired by the iterative projection-based approach implemented in the IDT algorithm and slice versus time distance. The idea of IDT, when it is used, the optimal transport in 1D, in the projection approach, use optimal transport, this equation. By definition, it doesn't take into account any available information about correspondences into formulation. It's non-parametric transformation function. And taking account of the available correspondences would actually guide the transfer process and improve the results. Also, optimal transport is increasing by definition, and it is not smooth. So here in this work, we propose to replace altogether optimal transport function, and we replace it by using the Nadaraya-Watson estimator that takes directly the advantage of the correspondences into formulation. So in 1D, the Nadaraya-Watson computes the estimated of an expectation of U giving V using a kernel like the Gaussian. So this is the kernel. We choose it as a Gaussian with a bandwidth H. This bandwidth controls the smoothness of the estimated function. Here, Nadaraya-Watson makes use of local weights, such as that the estimated value of a function at point X must be influenced mostly by the observation near X. And so it's like, can be seen like a locally weighted average of all Y's. The Y's that near X have a higher weight, and the Y's that far away from X have a lower weight. And the kernel here is treated as the weighting function here. And the bandwidth H is the hyperparameter or its scale that need to optimize. And, you know, as I said before, control the smoothness of the estimated function. Here, this figure compare between the optimal transport and Nadaraya-Watson. This estimated as part of one iteration of our algorithm. We can see the optimal transport, the blue line is increasing by definition and doesn't take into account any correspondences. And the line with Nadaraya-Watson is non-monotonic and does, guided by the correspondences available. Here, the visual, we can see the IDT, the optimal transport, try to match the source to the target, unsuccessful. And the Nadaraya-Watson actually give a better result because it takes into account the correspondences. So our pipeline, there's similar steps. We create batch correspondences, the same thing with SIFT Flow descriptors. And the difference here, we have correspondences here, and we deal with the correspondences as them, not like optimal transport that treated them as a separate. So Nadaraya-Watson take into account these correspondences. So at every iteration, we project the points that is in high dimensional 1D subspaces, and we find the 1D solution using the Nadaraya-Watson and propagate back the solution to the high dimension, and we repeat until convergence. The next step is merge recolor candidate. Here, the results. Our approach denoted here by the NW, that means Nadaraya-Watson. C is like using color only, and CB is combined color and position. In conclusion, the quantitative metrics showed that our algorithm, that is Nadaraya-Watson, performs similarly with top algorithms, that is BMLS and L2, and our two previous approach. All the metrics here show that Nadaraya-Watson using color only or combined color and position takes the correspondences into account, significantly outperform the optimal transport function that doesn't take into account the correspondences. You can refer to the thesis for details analysis. In our algorithm, the Nadaraya-Watson iterative approach, we use the problem in 45-dimensional space. The qualitative analysis here, both Nadaraya-Watson solution using color and combined color and position are successful in eliminating the elevating the column differences compared with the state of the art, and definitely outperform the optimal transport. But because Nadaraya-Watson is very smooth function, sometimes affect the exact color mapping, which in this case makes our approach that use optimal, smooth optimal transport with SIFT Flow is the best in elevating these color mapping differences. And here in this photo, our algorithm with Nadaraya-Watson is robust to registration errors. And our first approach that creates this shadow when there is a big changes between the images, the Nadaraya-Watson doesn't produce this shadow artifacts. And Nadaraya-Watson approach can create a smoother color transfer results and remove the JPEG compression artifact and noise. The last work is sliced L2 distance for color grading. So we have seen, and we can see in the literature, that optimal transport has been successfully used as a way for defining cost function for optimization when performing color transfer distribution. But there is more recently an efficient framework for color transfer was proposed for registering directly multi-dimensional Gaussian mixture models that capture the target and the source data sets using the L2 distance. This framework relies on a parametric formulation for the mapping with thin plate spline. That pushes the source image to the target image ones. This framework has been shown to be competitive with the alternative optimal transport-based solution. But one problem in this framework is doesn't scale well in high dimensional spaces due to the increase in computation complexity associated with the increase of data dimensionality. So far, in the 1D projection approach, the optimal transport has been used, but it doesn't take into account when computing the solution, available information about correspondences. And the mapping is increasing function by definition, as shown in the graph. So optimal transform is the red line. And our recent research efforts have extending the IDT and slice versus time distance projection-based algorithm using actually image batches as samples in higher dimensional space rather than the RGB triplet in R3, and taking advantage of the correspondences between the source and the target using the kernel regression, the Nadaraya-Watson estimator. But the optimal transport and Nadaraya-Watson estimator are, by definition, they are non-parametric function. They have no parametric formulation of the solution. So this limits the possibility of applying this transformation to previously unseen values, such as recoloring multiple frames in a video. So if we have a video, we want to estimate the transformation from the first, using, for example, the first image, the first frame, and we want to automatically apply that transformation to the rest. We don't want to repeat all that, estimate for the rest of the image. It's unfeasible. So we cannot do that directly with optimal transport and kernel regression because it's non-parametric function. We can invent a workaround, solution like estimate template on top of them, but itself, the optimal transport, there is no parametric formulation, and kernel regression, the Nadaraya-Watson, there is no parametric formulation, so we cannot apply the transformation directly. So in this paper, we propose to extend this projection-based strategy using the robust L2 distance to infer the function suitable with and without correspondences. And the function is parametric. So it's a parametric function. So we propose to replace the optimal transport altogether in the projective approach by following parametric, non-rigid 1D transformation model, where UL here is the control point, phi here is the radial basis function, and the theta here is the parameters that control this transformation, which is estimated by minimizing L2 distance between the source and the target distributions. The probability density function F is 1D Gaussian mixture model fitted to the source sample, and the BDFG is 1D Gaussian mixture fitted to the target samples. Using the 1D projective strategy allows us in this setting to tackle the inherent limitation of the template spline parametric formulation that doesn't scale well in high dimensional spaces. And the graph here shows the behavior of L2 with and without correspondences. So L2 framework can work with and without correspondences. Our pipeline is the same. We extract batch correspondences using SIFT Flow algorithm to take, since we can use the correspondences directly, so we extract them using the SIFT Flow algorithm, and we create the overlapping neighborhood and the high dimensional point descriptors, and when we go to 1D subspaces, we use the L2 framework to estimate the parametric mapping function. And after the transformation, we merge the recolored candidate and produce the final output recolored image. Please do refer to, I omit a lot of details here because the time, but you can find in the thesis how we estimate the Gaussian mixture models and how we compute the LT distance and all the optimization and also the analysis in the thesis. Here in the results, our approach, we denoted by sliced L2 distance. And when we use the color, we put C letter refer to using color only, and CB refer to using combined color and spatial. And when we use the correspondences, we put the word CORR, and we omit the word when we don't take into account the correspondences. This is how we denote it in the results, each algorithm. In terms of metrics, the sliced L2 with correspondences, with correspondences, whether like using color or combined color and spatial information, significantly outperform the sliced L2 when we do not use correspondences. Also, when we combine color and spatial information, it improved the performances of using color only. So you can see, with the recoloring, you can match the recolor boxes. And also the iterative projection using L2, taking the account or the advantage of available correspondences, outperform the IDT, the iterative projection approach with the optimal transport, which is IDT. And using statistical tests, we found that the median reported by the techniques BMLL, the top techniques, BMLS and L2 and our previous approach, they have equivalent quantitative performance. We solved the problem in 45-dimensional space. Here in this figure, we present the qualitative evaluation. We pick the result of the method that scored the highest value, quantitative values, and compare visually with their results. L2 distance are robust to registration errors and do not introduce visual artifacts. Also, we found the result of L2 that account for correspondences are very similar visually to the Nadaraya-Watson approach. Because they are both smooth function and they both account for correspondences. The difference now here, the function itself, the framework, and also Nadaraya is non-parametric, and L2 now framework is parametric. Also, L2 distance solution with the 1D projective approach can create smooth color transfer results, even smoother than the full L2 in 3D space, 3D color space. You can see that our results are smoother and elevate the JPEG compression artifacts and noise. This slide shows the time complexity of our algorithm for comparison. The 1D iterative projection approach involves iterative projection of database visually values that is originally in high dimensional space. We project them to 1D subspace and solve the 1D transformation function and then propagate the solution back. So each 1D transformation function, so we have iterative algorithms, and these are the time complexity. So our iterative approach is suitable for parallel computation and can run, all the 1D transformation can run independently for each pixel. So when we use the optimal transport, if we use the cumulative distributions, the CDF matching, time big of K is here is the number of the algorithm iterations. And if we use the quantile matching, this, using the sort, a fast sort algorithm, it takes big O of n log n multiplied by K, where n is the number of the samples in the dataset. This is because we are using the sorting technique. We sort the dataset, so it takes this amount of time complexity. And the Nadaraya-Watson take big of K. This is the iteration of the algorithms, and into there is an R multiplied by K. So because we in each 1D transformation function, it is a parametric function, so we estimate the parameters. So R is the number of iterations in the optimization function choosing to estimate the parameters. One last note, the actual execution time of the algorithm typically relies on the programming language and the style of implementation and the hardware resources. Our approach here, as you can see, is similar, looks like a neural networks. So it's similar to a neural network architecture. Hence, we can use the same strategy of implementing the neural network using libraries such as PyTorch and TensorFlow that uses GPUs. However, in our approach, the difference is we are not learning the projection, the weights, as in neural network do. We, in fact, learn a more complex activation function. And the task of optimizing the implementation specifics using neural network libraries is left for a future work. These are our publications, and I put a link for my thesis at the last line here. Thank you.